many different parameters. It's really a very simple method to use. Okay, so in practice, I would say that you would need to use random forest at least as a baseline for more involved statistical analysis. So in practice, random forests are really good, but in theory, we do not yet understand why random forests are so good. So the aim of the presentation is to present you some results, theoretical results, trying to understand how the algorithm works and why it has so good performances in practice. Okay. Different random forest models. So the idea of this model, so these are three types of random forest. So the idea, ideally, what we would like to do would be to analyze the algorithm which is used in practice. But it turns out that this algorithm, because it has really good performances, is also really complicated to analyze in theory. So we will try to look at more simple version of random forest. So we will try to simplify in some way the random forest algorithm. And we will do that in three different ways. So with the study of Sontag Forest, median forest, and Mondrian forest, which are three different ways to simplify the original algorithm, in order to say different things about these algorithms. And what we hope is that we are able also to say some interesting things about the original algorithm used in practice. Okay, so the plan of the presentation is as follows. First, a presentation of the algorithm, the original one, and then three different versions of random forest. Okay. No, loopé. Okay, so the general settings of the presentation would be this one. So here I could spend the whole presentation trying to present you a result for classification and for regression, and do that during the whole presentation, but it will be really complicated to do, so I will stick to the regression framework, where the aim is to predict an output which is continuous. So let's stick with the example of the price values of apartments in Manhattan of whatever you want, but the price value of apartment. So you have X, which are the descriptors of your apartment, and Y, which is the value of the apartment. And what we would like to do is to find the connection between X and Y, the connection between the descriptors of the apartment. So, for example, the surface, I don't know, the level of the apartment, the position, the exact position of the apartment, every descriptors you want, and the connection with that and the output, which is the value of the apartment. So what you're really interested in is the function m, which is the connection between x and y. If I have a way to estimate this function here, if I give you a new x, which is a new apartment, I will be able to build a prediction. So here, because we're interested only in prediction, our aim is only to estimate this function. Okay. And I will still assume during the whole presentation that my data, the input, are belonging to the hypercube 0, 1. Okay, it's not, of course, in practice, you do not have to assume this, you do not have to assume that, but in theory, it's much more easy to do. Okay. Is the presentation clear, roughly? Yes? Okay, I will have some, okay. So first, how do we build a tree? So here we try to understand how a random forest is built. So to build a random forest, we first need to see how we need to build trees. So let's look at this simple example where you have only a few data points, so 11 here, and x here is just bidimensional. So you have one variable, which is this one, which is renormalized between 0 and 1. The other one, which is this one, between 0 and 1, 2. And so this is the x, x1, x2, and y. So if I give you x1 here and x2 here, the y value associated to this x is 70. Okay. So here you have a very simple data set. In practice, you can think of like 1,000 observations, so 1,000 points, and many 1,000 or even more variables. So here you just have two input variables, and 11 data points. So here in the data set, so we just need to see how we build a tree. So to build a tree, okay, we first start with this cell, okay, and we're going to split. So the only thing you need to remember about a tree is that it's just a recursive way to split your partition. So you will start with this partition, okay, and then build a split in this way. For example, I did not tell you yet how I build a split, okay. Let's say that just we have a split, which is this one, and then you see that you end up with a cell here and another one here. So basically, you start with one cell, you end up with two cells. So you can do, if you have a way to build a split, you can do exactly the same thing, but in the two resulting cells. So in this one and this one. So you can do that again and again, and then at some point you stop. I do not mention yet how we stop. Okay. So assume just for now that we have a way to split and a way to stop. If you have that, then my question would be, if I have a new data point here, which falls in this cell, what will be the prediction associated to this data point? Okay, so if I have built the partition in like a relevant way, I would hope that the points that belong to a same cell, this cell for example, these points are close together in some sense. So a natural way to do for computing this prediction would be to compute something which depends only on the points that fall into this cell. So here what I can compute, for example, is the mean, the average of points belonging to this cell. Okay, so I will predict 85. I have different ways. I could build different prediction. Okay, I can compute the median, whatever things you want, but by default it's the mean. Is it clear so far? So I just need to mention two things. The first thing would be how I split, and second thing would be how I stop. So the way I split is just like very natural. Is I try to build a cell in order to build resulting cells that are homogeneous. That is, cells in which the values of y are close to each other. Because at first, what I want to do, okay, here I would like to regroup the values of y that are large and the values of y that are small, for example. So if you look at this observation, you see that on the left you have large value for y, and on the right you have low value for y. So a natural way to try to build groups of observation would be to gather the y's that are roughly the same. So here, okay, this is like a way to split in order to make homogeneous cells. So if you want to compute exactly the criterion which is used, is like you compute the variance in the left cell, the variance in the right cell in terms of y, and you compute the average, the weighted average of variance, meaning that you compute the probability of belonging to the left cell, which is just a fraction of points that fall into the left cell, the fraction of points that falls into the right cell, and what you do is the empirical probability of falling into the left cell times the variance in the left cell plus the probability of falling into the right cell times the variance in the right cell. So it's like a weighted average of variance in the two resulting cells, or you can see also that as an estimation of the error of the estimate, which is constant in the left cell and constant in the right cell. It's the same. So basically, what you need to remember is that we build split in order to make homogeneous cells in terms of y. So this is the first thing, and then we need to see how we stop. So here we stop with specifying a parameter which is called node size, which is the maximum number of observation you allow in each cell of the partition. So here you see in this partition that I have exactly 1 or 2 observations in each cell, in each terminal node. So you see that node size here is equal to 2, meaning that I have at most 2 observations in each terminal node. So it's a way to stop. By default, in the real random forest algorithm, it would be node size equal to 5. Is this construction clear so far? Yeah. A question maybe? Usually there is a question at this point, so I've made statistics. But if not, yeah. Feel free. Yeah. Oh, yeah. So this is a very good question. So what I will present here is like a compromise between the theory and practice. So in theory, I will need to assume that my data belong to 0, 1. But in practice, what you can do is either rescaling by the maximum value of your sample and the minimum value of your sample. What you can also do is computing the empirical cumulative distribution function of your data, which allows you to map any distribution into 0, 1. There are two different ways, but in practice, I would say that your construction is invariant by any monotonous transformation of each variable. So you will just let the variable or let the original variable in the algorithm in practice. Okay, so you do not need in practice you do not need to transform them. In theory, I will always assume that they belong to 0, 1. Okay. Other question? Yeah. Yeah. Yes. These two. Yeah. No oblique lines. There are many reasons for that. So you have procedures that allows for oblique splits. Computationally speaking, it will be really time consuming because you will need to compute d+1 coefficient instead of 1 coefficient here. Plus, it's not really clear when it would be a good thing to do to consider this oblique splits. Sorry. And that thing, yeah. And if you want to have an idea of which variable is important into your construction, it's easier with this construction because you can say, for example, in the first split, that okay, the first variable is important. If you start considering splits that are oblique, then I really don't know what would be important, what important would mean. Yeah. If the sample is wider, you said. So can you repeat? Mm-hmm. Oh, you can just compute. So by default, it's just 1/n. So the size of the data set, but you can put weights in the procedure. It would just mean that the criterion I have told you about the variance, the weighted variance, would be weighted in some different ways. Okay, so this is for the tree construction. So, but we need to build a forest. So at some point, we need to build many trees. And here, if I give you one data set, I just end up with one tree. And so, of course, I can build many trees which are exactly the same, but you see that you've lost something in the forest. Okay, the forest is too simple. So you need to introduce a way to build many trees. One way is to say that I will try to build many different data sets, because I know that from one data set I'm able to build a tree. So if I have many data sets, I'm able to build many trees. So a way to do so is simple: to resample the data set. Okay, so from one data set I end up with many different data sets. And here in random forest, I will consider, so by default, bootstrap is considered, which is taking n observation out of n with replacement. So from the n observation in the original dataset, I take exactly the same number of observation, but I allow an observation to be present many times in the new dataset. Okay, so it's a way to subsample. You can also think of many different ways, but it's the one by default in the procedure. So in this way, you end up from one dataset, you may build many different datasets, and on each one you may build a tree. Okay, so this would be really simple, but the procedure is a little bit more complex because in each cell of the tree, instead of choosing like the best split in each direction, in each variable, and in each position, what you're going to do is in each cell, randomly select a small number of variables, and then you're going to optimize the split only along these variables. So for example, I will have typically a parameter which is called mtry, which is, for example, equal to 1. It would mean that in each cell, I will randomly choose one variable and I only optimize the splits along this variable. Okay, I do not consider the other one. So in this way, I introduce a lot of randomness into the tree construction. So it allows me to build many different trees. Okay, so you have two steps of introducing randomness. First one is sampling the dataset, and second one would be like sampling the variable in each step of the tree, because we select in each cell a small number, or small or not so small, a number of variables, which is called mtry. Is that clear? So if you do that, you end up with a tree. So you resample the data set. In each cell, you do the randomization with the variables, then you end up with the prediction here. So this is how I will call the prediction in X. X typically is the red point before. So here it's the prediction in X given by the first tree, which is represented by the random variable theta1, which account for the resampling of the dataset and the sampling of variable in each node of my tree. So this is the prediction for the first tree, this is the prediction for the second tree, etc. And then you need to gather this prediction to build just one prediction, which will be the forest prediction. And here just compute, again, the average, the mean of all these values. Okay, in this way, you end up with the forest prediction. Is that clear? Maybe another question at this point? No? Everything is perfectly clear. Good. Oh, no, a question, yeah. Yeah. So in the, if you look at what you get in practice, no. Using Bootstrap, so typically what you want to compare, so I cannot compare many different procedures, but typically you can compare Bootstrap and subsampling. Okay, when you take just a small fraction of the data set, you can optimize. So you can optimize the fraction of points you take, and it would do like a little. You use procedures you end up with is a little bit more accurate than using Bootstrap, but there is no huge difference. So I would say that by default, using Bootstrap is a good thing to do, and you have no results in practice, at least, no examples that shows you that you need to do other things than Bootstrap. And in theory, I mean, studying Bootstrap is really complicated, so we prefer to analyze subsampling. Okay. So again, the procedure is as follows. To build many trees, we're going to select AN observation. Typically, here I consider AN because I will allow to select a number of observation which is lower than the original number of observation. So I would do subsampling. And then here I use only this observation to build a tree. In each cell, I randomly select a small number of variables and I optimize the split only along these variables here. And I do that again and again until the stopping criterion is met for all cells. Small review of literature. So random forest is like a recent procedure in statistics because it's from 2001 by Riemann. At first, when you look at results, theoretical results that try to analyze random forest, they focused on a simplified version of random forest, which are typically built without the dataset, meaning that you have your dataset, you do not look anymore at your dataset, you build a partition, which doesn't depend at all on the dataset, meaning, for example, that you're going to build a partition which is where you select randomly a variable, uniformly a variable among the d variable available. Then you're going to split in the center, for example, of the cell. Exactly in the center, you're going to have two resulting cells, and you're going to do that again and again. And then at the end, when you ask yourself, what is the prediction? Then you are quite annoyed because you have no value for y. So what you need to do is to put back the data into the partition in order to build an estimation of y. So it is an estimation of the mean value of y in each cell. So in each cell, you're going to compute the mean value of y, and this will give you the prediction into each cell. But in this particular construction, the values x and y are not used to build the partitions. They are only used at the end to estimate, to build the value, the mean value of y into each cell. Okay? So this is a really strong difference between this forest. There is a really strong difference between this forest and Breimann's forest, because in Breimann's forest you use both the positions of the points and the values of the points to build the split, which is optimized in some sense. So this was for the first results, and this is currently an active domain of research, but you have also results that focused on more data-dependent forests, where the dataset is used in this forest to build the partitions. And you have so many different results, but all these results, in all these results, you have some kind of assumption which are related to the way trees are built, which means roughly that trees should not be like adversarial, or at least the dataset should not be adversarial. So you do not want, you may have really particular behavior of the trees, and you want to avoid this. So basically, you will assume that either the construction, the partition of the tree is robust compared to the dataset, meaning that if I change a little bit the value of an observation in the dataset, it won't change too much the partition of the tree. But I have no way to assess that in theory. I can do simulation in practice, but I have no way to assess that assumption in theory. Or I can assume that it leaves, for each split, it will leave a small fraction of data points in the left cell or in the right cell. But again, and I have no way to prove that in theory, because the procedure of Braymans is as it is, okay, and I cannot put assumption on that. So all these results must be taken with cautiousness. Yeah. And for the end, so really nice theoretical review here, and also really nice theoretical review here, but from a methodological point of view. So really, how you need to use random forest in practice in different fields. Okay. So good. In the remaining time, I will focus on the 3 different random forest model. Okay. So first one would be the Sontag Forest, where, as I mentioned before, so it's a forest which was construction does not depend at all on data. So you're going to randomly select a direction to split, and then split at the center of the cell. And you're going to do that again and again. So this forest is like, the construction is independent of X and Y. So it's a very simple forest in some sense. And we can say many different things about this forest, because we can compute many probabilities, many rates of consistency, and it's actually computing a rate of consistency, maybe not the sharpest one, but at least a rate of consistency is actually really simple for this kind of forest. So it's really like the nicest forest you can think of. On the other end of the spectrum, you have the Braymans forest, which is really difficult to analyze because it depends on both X and Y, the position and the value of the point. And it's like it's the forest we want to analyze, but it's really complicated in theory. So we try to find a forest which is a good compromise between both. So here you can say that the forest may depend on X or may depend on Y. And it turns out that it's much more amenable to analysis when the forest depends only on X, only on the position of the points and not on the value of the points. So here, median forest will depend only on X. The construction will be totally independent of Y, and we hope that this will lead us to some nice result about this forest and also about Braymans forest. And in the end, maybe we can have a look to Mondrian forest. Okay, so we start with Sontag Forest, so the most simple forest you can think of. So again, you're going to choose randomly a variable and split at the center of this variable, and do that several number of times, and stop at some point. So first, the general result. So here we will only be interested into consistency, which is this property, which means that here you have the estimation in X, so it's a prediction given by your algorithm, and what you want to prove is that the prediction here is close enough to the true value of the function when the number of samples tends to infinity. So basically it means that if you have a huge data set, then your prediction is going to be close to the reality. Okay. It's like the basic property you can ask to a learning algorithm, because if you do not have this one, it means that you're not estimating a good quantity. Okay. And it's like it's a very basic one, because in practice you do not have a data set which tends to infinity. So this property is only here to assure that the algorithm asymptotically is doing a good job. It's not here to compare algorithms, it's just here to say that this algorithm works in some sense. Okay, so if you look at this theorem is about trees whose construction is totally independent of data. Okay, so I have my data, I throw them away, and I build a partition. So the question is now when this partition is consistent, meaning when a single tree, estimate the true function with a very good precision. So you need to require two things. First one is about the diameter of the cell here. So this is the diameter of the cell AN, X, which is the cell of the tree which contains X. Okay. So here you have to assume that the diameter of the cells tends to 0 in probability, which means that when you have a huge, when your number of data is growing to infinity, then the cell's diameter is tending to 0. Okay. And the second one is the fact that you need to have a large number of observations in the cell. This is a number of observations in the cell ANX, so the cell of the tree which contains X. And this number must tend to infinity. So it means that when the number of observations is growing, then I must have in each cell a growing number of observations. So here the first assumption is here to ensure that the approximation error of your estimator is tending to 0. Approximation error means that so you need to recall that in each cell, you're going to estimate your function by a constant function because you're computing a mean in each cell. So it means that wherever you are in the cell, your prediction is the same. Okay, but maybe the true function m varies in the cell. So you have some error which is related to the fact that you have some difference between the function m and the best constant function in the cell. And to ensure that this error will tend to 0, then you need to have this kind of assumption because you know that if you look close enough to a function, then the function is almost constant. Okay, so for example, if I consider cells that are tending to 0, then it's a well way to approximate any function to consider a constant function. Okay, so basically, first assumption will take care of this problem, and second assumption is here to control the estimation error, meaning that I talked before about the best constant function I can put in the cell, but of course I do not know the best constant function because it would depend on the distribution of x, y, the joint distribution of x and y. Here what I can do is computing the difference between the mean of y, which is the prediction of the algorithm, and the best constant in my cell. And this allows to say that the difference tends to 0 when n tends to infinity. Okay, because basically it will say that I'm well estimating the expectation of y given the fact that x falls into this cell by the mean value of y, the empirical mean value of y into this cell. Okay. So basically it's a term of approximation related to the variation of the function, and here a term of estimation related to the number of observations you have because you do not have access to the true distribution of your problem. So it's like, I would say that this is like a really nice theorem because it's really simple and you do not have many extra assumptions. Assumptions are really understandable. Yeah, question. So, good question. So this construction, the fact that you have, how to say that? So the fact that you are able to divide, so for any squared error of your estimate, you are able to say that this error is a term of estimation and a term of approximation. When you allow, and you have more precise expression when you're looking at which is called local averaging estimates, which are estimates where you just compute some weighted sum of the y's in order to predict. So for this estimate, trees and forests, you have some really nice way to compute to upper bound the error, to upper bound this quantity. This bound is no longer true when you allow the partition to be data dependent, because you will have typically some extra terms that comes into play, and that correspond to the fact that you use the same data to compute the mean and to build the prediction, which is like which can be related to another fitting problem, because basically you're using your data to do two different things. So when you do that, you must be sure that, how to say, that the procedure is either the data are not adversarial, or the construction of the tree is not adversarial, because you can, if you're really unlucky, maybe you end up with a construction that really works in a general case, but won't work in this one. So it's like general answer, but I would say that the basic idea is the fact that when you have trees that are built using data, it's like related to overfitting problem, because you use your data both, and it's really complicated because you have some really complicated dependencies between a split and the splits that come before. Okay. But it's true that you have you have this kind of result for trees whose construction is dependent of data, but you will have to put extra assumption than these two ones, because you need to assume that the partition is not too complicated. So it is related to like the number of way you have to partition the data. If I consider any general tree, so it's really more complicated because you need to take into account how you split the data and what kind of different sets you can build, what kind of different partition you can build for the data. Okay, general answer. More questions? Okay. So Sontag Forest. So again, the Sontag Forest is as follows. So you start with a tree, you choose a direction, you split. Okay, you build two cells, and then you're going to split again, choosing maybe two different directions, and splitting again, and you're going to stop at some level k. Here k is the number of times you have split each cell, and also called the level of the tree, with all the depths of the tree. Sorry. So you have a theorem telling you that this forest, so if you consider central trees and you average central trees, you have a theorem telling you that this forest is consistent provided two things. The first one is k tending to infinity, which says that the tree, when you increase the number of observations, you must have the level of the tree which grows to infinity, which means that this will allow to have partitions where cells have a diameter which tends to 0. Okay, because here you see that when you've selected a direction, you divide by 2 the diameter along this direction. So it's like, on average, it's easy to see that the diameter is going to 0 when k tends to infinity. And second assumption is the fact that n over 2 power k tends to infinity. So maybe this one is a little bit more complicated. But here n is the total number of observations. 2 power k, because you have a full binary tree of level k. 2 power k is the number of cells you have, of terminal node you have in the end of the tree. So n over 2 power k is like the average number of points in each cell. So what you are asking here is that the average number of points in each cell is tending to infinity, which is roughly as the assumption before, which says that in each cell you must have a number of observations which tends to infinity. So basically this theorem is like the equivalent theorem, but for random forest. Okay. Bad thing is that this, the consistency of the forest here just results from the consistency of the tree. So basically it says that the tree is consistent, then the forest is consistent. So I do not have any benefit of using a forest instead of a tree here, because I have consistency for a tree and consistency for random forest. And a second bad thing is that here the aim, you must remember the original aim, which was to analyze Bradman's forest, but in Bradman's forest you have a small number of points in each cell. Okay. Here I assume that you have a huge number of points in each cell, because this number is tending to infinity. Okay, so this is really a huge difference, and besides, the construction of the forest is totally different. Okay, so basically it's a good thing, because we know that it's not. So we know that centered random forest works because they are consistent, but that's it. Questions so far on Sontag Forest? Yeah. So I have a very nice answer, theoretically speaking, because what I will assume typically is that I have a density for x. So with probability 0, I have the fact that a line crosses a point with probability 0. And in practice, you are not going to use Sontag Forest, so I have the answer both in theory and in practice. Okay. Okay. So for median forest now. So let's look at the construction of a tree. So this is just the construction of the Brayman tree, okay? So the original algorithm. And then I will modify this construction in the following way. So I assume that you have, again, to build a tree, I select AN observation without replacement. Okay, so this is almost the same thing, but here it's without, here it's with replacement. Okay, so, and only those observations are going to be used to build a tree. Okay, then to build a tree, here's a strong difference. At each step, when in each cell, what I will do is that I will select randomly a variable, just one variable, okay, and I will split, not in order to maximize some criterion which depend on y and x. Here I want to build a forest which depends only on x. So I will split so that the position is at the empirical median of x. So it means basically that I will allow for the split to have a left cell and a right cell which contains the same number of points. Okay. And since here I split according to x, according to the position x, then I can assure, by doing that again and again, I can stop when I have exactly one observation in each cell. I could not do that for the Sontag Forest because if you remember, Sontag Forest, I've thrown away the data when I built the partition. So I cannot stop when I have just one observation because at the time of the construction, I do not see the observations. Here, I just remember the position of the points in the construction process, so I can stop exactly when I have one observation in each cell. So you see here that this forest is more close to Brayman's forest because I have exactly 1 point, so a small number of points in each terminal node. So a theorem. So just for now, not look at the assumption. So the assumption is like a regression model as before and some technical assumption here. Then, providing we get the consistency of the forest. So this is like the estimation given by the forest at x. And this is a true function, so it means that the forest is consistent. Okay, so in the end, it was the result we want to obtain. And so now we can look at the two main assumptions, which is an tends to infinity and an over n tends to 0. An tends to infinity means that an is the number of points I select to build each tree. So it means that for each tree, I must build each tree with a growing number of observations. Okay, this is rather logical because in statistics you have n which tends to infinity. If a tree only sees one observation, it's not going to be consistent at all. Okay, so it's like a basic requirement. So I would say that this assumption is really logical. And the second one is a little bit more tricky. It's an over n which tends to 0. So an is the number of points I select for each tree. So I build a tree only on an observation, but the whole data set is of n observation. So an over n is a fraction, the percentage of points used to build a tree. So by requiring that an over n tends to 0, it means that each tree is built with a small fraction of the original data set. So you can think of this condition as a way to ensure that trees are diverse enough in the forest, because each tree is going to be built with a different part of the data set. So because you have an over n which tends to 0. So each tree is going to be built with a small fraction of the data set. So with high probability, each tree is going to be built with a different part of the data set. Okay? So this is a way to ensure that trees are different enough, because of course, if you have a range over many trees which are the same, then you lose the gain of the forest. So it's a way to ensure that trees are different enough in the forest so that there is an averaging effect in the forest. And here you can see, so with these two conditions, you can see that the forest is consistent, but you can also see that for this construction, a single tree is not consistent. You can prove that the construction I've described before of a median tree is not consistent because you leave only one point in the terminal nodes. And you have a theorem telling you that it's not consistent. So basically here you've taken a tree, a single tree which is inconsistent, and you've turned that into a forest which is consistent just by averaging. Okay? So here you see that you have again a benefit of the forest compared to a tree. You have an inconsistent procedure, a single learner, a tree which is inconsistent, and a forest which is just the averaging of the trees which is consistent. So here you have a benefit. The theory explains that you have a benefit of the forest compared to just a single tree. And this was what we were interested in the beginning. Okay. Plus, throwing on the bonus, it would be that here you look at fully grown trees, meaning that you have just one observation in the leaf. And here it's really close to Bregman's forest. So you can, the idea is to say, okay, we have a procedure which is a simplification of Bregman's forest, but here you see that you have an effect related to the averaging. So maybe in Bregman's forest it's the same. Of course, we did not analyze exactly Bregman's forest, and this construction is far away from Bregman's forest, but maybe the conclusion is the same. Okay? Or from a theoretical point of view, maybe not, but at least this theorem is true for median forest. Okay. A question maybe? Nope. Yes? Arnaud? No? No question? 5 minutes? I would have preferred the question. Yes? It's whatever. It's a tree. So because here you have an which tends to infinity. So either you consider a tree built with an observation, or you can consider a tree built with an observation, but growing to the full depth, meaning that a tree, the basis of the result is to say that a tree which is fully grown is not consistent. Yes. So you mean you leave a small percentage of the original dataset into each? Yeah, you can do that. So actually, I don't present here, but I have a general result for this kind of tree. But where you can add an extra parameter, which would be the depth of the tree, k, and I have an upper bound for the rate of consistency for this tree. So you can consider a tree where you stop earlier in the tree construction, and this tree would be consistent. And the forest is consistent too. But what I was really interested in this result would be to have a tree, an inconsistent tree, and a consistent forest. But if you want to have a consistent tree, yeah, you can leave a high number of observation. And in this case, if you're just interested in consistency, you can apply the theorem before, because what I didn't mention is that the theorem is almost true for partitions that depends only on x. So you just have one more technical assumption, but the theorem is almost exactly the same. More question? Either more question, or I try to introduce Mondrian forest in like 2 minutes. As you wish. Okay, so Mondrian forest. So here the construction is so we've seen Sontag Forest, median forest, and now it's Mondrian forest. So maybe so just here it remains 3 minutes. 3 minutes remaining. 4. Okay. So okay. So the construction of the trees is as follows. So the idea is to have a time-dependent construction. So here you will start with a cell which is again 0, 0, 1 square, and what you're going to do is to have times of splitting for each cell. So here you see that you have the tree structure, and here you see that this cell, the first cell, is split at time 1.3. And for each cell, so I split the first one, then I obtain 2 cells, and this one is going to split here at times 2.3, and this one is going to be split here at times 2.7. And then I do that again and again until I reach a time which is a lifetime of the partition, which is called lambda here, and which is 3.4 in this example, meaning that all splits that occur after the time 3.4 are discarded. I do not take them into account in the tree construction. So it's a way to specify, to stop the tree construction. Before, we've seen ways which were related to the number of observation or to the depth of the tree. Here it's like the depth of the tree, but you see that you can have trees that are not binary and fully, not binary, yes, but not fully grown, not complete, sorry, because you may have different number of splits for different cells. It is clear, roughly? Yeah. So now I just need to specify how I choose the time, how I choose the splitting points. So the time is chosen with an exponential variable. So for each cell, when the cell, so at the beginning I would choose an exponential, which is of parameter the half perimeter of the cell, which means that the parameter of the exponential grows with the size of the cell, meaning that if the cell is large, then I will have the cell is going to be likely to be split at an earlier time in the tree construction. Then if the splits, so imagine that I have chosen E, which is my time of splitting. So if E is lower than lambda, or to put it differently, if the splits occur before the lifetime of the partition, then I will indeed make the split. And I do the split in the following way. I will choose a coordinate j with this priority, which is not uniform compared to before. It depends on the length of the side, of the j side here. bj minus ij is the length of the side along j. And here, once I've done that, then I will choose a uniform position along this side. Okay? So if you're not following so far, just imagine that you have a tree construction. And then what you can ask is what are the rate of consistency for this partition. And it turns out that main result is that if you consider a random forest, here you have the fact that the random forest is reaching optimal rate for Lipschitz function. So if you assume that you have your function m, your true function m is regular enough, meaning Lipschitz, then you have the fact that the rate of consistency here for Mondrian forest is the best one you can imagine. Okay, so this procedure belongs to the class of optimal procedure for Lipschitz function. Then, so this was like the first result for optimality of random forest. So before this result, we did not know that random forest could be optimal for Lipschitz function. So yeah, but a good question would be here is to say, so from the beginning I've said that there is a difference between a tree and the forest. So here I would love to say that there is a difference between a Mondrian forest and just a tree, a Mondrian tree. But if you look at this expression, you see that m, the number of trees, does not appear here in the right expression. So basically this one is independent of the number of trees. So what you can do is ask, okay, so it means that trees and forests are the same for Mondrians? So it turns out that no. The reason is that if you look at functions that are 1 degree smoother than just Lipschitz function, so if you look at twice differentiable function, then you will end up, so the main result of the theorem is that for twice differentiable function, so this part, then you end up with a rate which is optimal for the forest. And the good thing is that it depends on the number of trees here. So it means that this rate is optimal if you choose m large enough. But it's not true if you choose m equal to 1, for example. So it means that for twice differentiable function, a tree is not optimal, but a forest is. So before, for the median, this will be the conclusion. For median, for Sontag Forest, you had no, For median forest, for Sontag Forest, you have no benefits of using the forest compared to a tree. For median forest, you have a benefit in terms of consistency. A single median tree is not consistent, but the forest is consistent. And here you have, for Mondrian forest, you have a benefit comparing the rate of consistency for twice differentiable function. A Mondrian tree is not optimal, but the forest is. So it's like looking, for median forest, we looked at the limit, okay, the consistency, and for Mondrian forest, we look at the rate of consistency. So this would be the conclusion, and I didn't present a result on the consistency of the original algorithm, but we have also this one. Thank you very much. Yeah, it's my microphone. And it doesn't work.
Bueno. I just wanted to ask, which one is the most used in practice? Which one is more useful?
Yeah. So very simple answer, because basically the three random forests I've presented are not used at all in practice. This is just to do theory. So to understand that you may have a benefit of using a forest compared to a tree. We didn't implement this forest because the main difference between those forests and Braimann's is the fact that for Braimann's forest you have a dependence on the criterion of the criterion on y, on the value on the output. And this will allow to have a procedure which is relevant in high dimension, because it will allow to select the relevant variable, the relevant input variable, to make a prediction. In median forest, you do not have this type of construction because you're choosing a variable randomly by not looking at data. So if you are in dimension like 1000, you may have to split many times your trees in order to just split along the relevant variables. So I would say that if you have an idea of how you may add a selection procedure inside median forest or Mondrian forest, it would work. Yeah, that would be my answer. So basically, this is just theory. I'm a statistician, so it's nice to do theory. But this is just to try to figure out what is the mechanism at work in the averaging process of a forest. Hola. Oh.
Bueno, okay. And this is a similar question to just the one that was asked. Seems like an advantage of these forests that do not use data is that because of your results, which are general for whatever function f,
Mm-hmm.
you can have like a universal tree for whatever data you have. So you have to, I mean, I'm thinking like maybe humanity only has to build one tree and use it for whatever estimation you can do.
So yeah, so this is the difference between the theory and the practice. So in theory, you have many algorithms that reach optimal rates of consistency, for example. So it means that the rates have so the rates here I've presented. So I just said that this is optimal, but you have many algorithms that reach these optimal rates of consistency. So having this result doesn't mean that the forest is the most powerful algorithm you know. It means that the forest is among the most powerful algorithms. So indeed, if you have a huge number of observations, then you will be able to estimate consistently your function. But if you are in high dimension, for example, you may need like, I don't know, 1 billion of billions observations in order to obtain an estimation which is precise enough. You see? So consistency and rate of consistency are true. Okay, the theory is here, so and it's solid, but it doesn't mean that this is the best way you know to approximate your function. And in particular, I will emphasize the fact that this algorithm lacks a way to select relevant variable to split. So this would be the strong difference between these algorithms, centered, median, and Mondrian forest, and Braimann's forest. In Braimann's, you have a way to build a split which depends on the variance of the y in the cells. So it means that the splits depends on the repartition of y, on the distribution of y, whereas here it doesn't depend at all on y, and this will make a strong difference in practice, because in practice you have okay, people gather data and data and data, so at the end you have many variables because they put all they know in the data set, and you have like 10,000 variables, maybe like 10 that are really relevant for the prediction, but you do not know that. So I would say that Bregman will do a good job, but this forest, without like an attention mechanism focusing on relevant variable, are not going to do well. Did I answer your question?
Yes, I think. Yeah, it's a good answer.
I have a question. Do we have time?
Yeah, we'll have time.
So yeah, you mentioned the Breiman's forest consistency and also some nice properties of forests, such as the handling of high-dimensional problems.
Mm-hmm.
But when would you advise against using Breiman's forest?
Against what?
Against using Breiman forests? When do they perform poorly, or when would you rather use something different? When do they perform
so
well?
it's not. I think if Bremen's forest don't work, I would say that all forests won't work, because I do not know a better way to split than Bremen's forest. You have modification that decrease the computational time for this forest, but not from an accuracy point of view. I would say that the major default of this procedure is the fact that the function is a stepwise constant, and in like problems where you know that the phenomenon is driven by some kind of differential equation or whatever, like an underlying phenomenon which is thought to be continuous or differentiable, then you do not want to use that because the prediction is going to be stepwise constant. I would say that this is a major, not default, but characteristic of the method, because at the end you end up with a prediction which is in this way. So if you know that the prediction is not constant by piecewise constant, that you do not use this method. Otherwise, I do not know. I have no particular insight.
There are no questions.
Thank you.
Vamos 10 minutos para café y calentar y regresamos. I don't know it, but I can share data if you want. will put the microphone on.
Thank you for being back. So, our next speaker and last speaker for this colloquium is Yarin Gal from University of Oxford. Yarin did his PhD with Garamani in Cambridge, I guess, and then he turned to be an assistant professor in Oxford University. He is also heading the Oxford Applied and Theoretical Machine Learning Group in this university. And he will speak today about Bayesian deep learning and space.
Thank you. Can you hear me? Is that okay? Yeah? Is that on? Yeah? Okay. Is that? Yeah? Okay. Yeah, okay. Yeah, so thank you for the invitation to give a talk here today. We're going to talk about Bayesian deep learning. I'm going to talk about space. I'm not an expert in astronomy, so a lot of the stuff over here do accept my apologies if I'm being a bit imprecise, but I had the fortune of collaborating with lots of pretty great collaborators in astronomy in the field. And basically, that's what I'm going to talk about today. I'm going to talk about a bunch of the works that we've done on the intersection of Bayesian deep learning and astronomy. So let me start with who knows what Bayesian deep learning is? Okay, very good. So it's an opportunity to explain what Bayesian deep learning is as well. So Bayesian deep learning is an intersection of two of the biggest pillars in machine learning. Two very, very big pillars in machine learning. One is Bayesian probabilistic modeling. The other one is deep learning. I'm going to give a very brief introduction to both of those things just to get everyone on the same page. So if you don't know what deep learning is, this is deep learning in one slide. If you do know what deep learning is, then I'm going to use that to introduce some notation. Deep learning is made of conceptually very simple models. We have, if you give me some data x and y, x a bunch of images, I'm going to assume everything is vectors for simplicity. Y is labels like cat, dog, cat, cat, dog. I'm going to build a model, which is basically going to be an affine transformation of x and then squash it through some nonlinear function, do another affine transformation. I'm going to get y tilde, and my task is to find some w's for which y tilde is as close as possible to y. That's deep learning. Deep learning is very useful. It is these very simple modular tools. We can build very big, complicated models. The field got huge attention from practitioners and engineers, which in turn built very good software tools that scale well with data and compute. And the field has had real-world impact. So whenever you hear someone in the news talking about Facebook using AI for that, Google using AI for that, they mostly mean that Facebook and Google and whoever else is using these sort of tools to do machine learning in applications. Deep learning also has lots of issues. So for example, we can't really tell what our models know, what we don't know. These models are fairly perceived to be uninterpretable black boxes, which are easily fooled, posing issues in AI safety. These models lack solid mathematical foundations. They're mostly developed based on ad hoc techniques, and they crucially rely on big data. Surprisingly, if you had uncertainty at hand, then you could answer all of these different questions. I'm not going to talk about the statistics side today. I'm going to talk more about the application side. So let me try to convince you why you need uncertainty. What is uncertainty and why you need uncertainty? So let's say that you build a dog classifier. You decide you have a brilliant idea. You're going to collect lots of pictures of dogs of different breeds, and you're going to build a dog breed classifier that you're going to put that online. You're going to people are going to go online and upload pictures of the dogs, and you're going to tell them which dog breed it is, and somehow you're going to make money out of that. I don't know how. And then some user is going to go online and they're going to upload a picture of, sorry, this like the direction over here very weird. Going to upload a picture of this. Now this is something that your model has never seen before. I don't know what that is. I don't want my model to say, I don't want my model to force that thing into some dog breed class. I would want my model to say, I don't know. I would want my model basically to say, it could be that dog, could be a golden retriever, but I've never seen that thing before, so I'm going to say, I'm going to give you high uncertainty for my prediction. This might sound like a contrived example, but we have exactly the same issues appearing again and again in decision making, in life sciences, in physics. If you have uncertainty, you can also use that, for example, to get better insight into when your deep model, when your black box fails. So this is actually an example of work that we did on autonomous driving, where we took a semantic segmentation system, the one that you use in a car to basically to tell that's a sidewalk, that's a car, that's a pedestrian, and basically ask it, what do you think, like where are you confident about your prediction, seeing that the model actually was very uncertain around the pedestrian and so on. You can basically use those sort of tools to get an insight into why your model is failing. Can even use these sort of tools to get an idea for when someone is trying to fool your model, someone is trying to give you an adversarial example. Lastly, you need much less label data if you only collect labels when your model is uncertain. That allows you to avoid wear and tear in robotics. It allows you to reduce expert time in medical analysis and so on. I'm going to talk about a bunch of applications related to these sort of topics, and specifically applications in astronomy. So this is very confusing. So how do we actually talk about uncertainty? The language of uncertainty is probability theory. Specifically, we're going to talk about Bayesian probability theory that has its origins in the 1750s due to Reverend Thomas Bayes. When we apply Bayesian probability theory to information engineering, we get what we call Bayesian modeling, where instead of looking for a single set of parameters that maximize probability for the data, we put a distribution over all possible parameters, and we basically ask what is the probability for different parameters, which are more likely, which ones are less likely, given some data. If you have some function and you have some inputs x and y pairs, then you can say this is a very likely function, these might be less likely functions, but we basically want all the functions. So Bayesian modeling is built on solid mathematical foundations, but it it's perceived as fairly orthogonal to deep learning. I'm gonna just hold it like that. So I'm gonna give you a very simple way of tying these two things together. I'm gonna talk about one simple way. There are a billion different ways to do that by now. The field of Bayesian deep learning, I think, is one of the, at least the workshop, the Bayesian deep learning workshop at NIPS, I think, is the second largest workshop at the conference. Has been the second largest workshop at the conference for the past 3-4 years. And there's been huge amount of research on getting lots of different ways of tying these Bayesian models and deep learning things together. I'm going to talk about only one way of doing that, a very simple way that intuitively, hopefully, will give you an idea of how these things are basically connected together. I'm going to talk about a tool called Dropout, which is a very popular method in deep learning, cited millions and millions of times by now. It's very simple. So if you take your This is confusing. If you take your neural network, so remember this was the input vector x, these are the elements in the input vector, it's affine transformation, we get a feature vector. All we do is basically we multiply these input elements by Bernoulli random variables, that's all. Or we randomly set these things to 0 probability 0.5, for example. And then you do the affine transformation, and then you randomly set these things to 0 probability 0.5. Then you do another affine transformation, and you get y. That's called the stochastic forward pass. Test time. At test time, basically what we do is we don't do dropout. We just take x, multiply by w, multiply by w, get y. That's called a deterministic forward pass. Now this technique somehow improves performance and reduces overfitting, uses almost all of modern deep learning. And it turns out that we can show that dropout training is identical to approximate inference in some Bayesian model. And this is actually a video of a dropout neural network fitting to this data set of like some data points. And you can see high uncertainty far away from the data, low uncertainty near the data. Each black line is a draw from the predicted distribution of functions. Each shade of blue is half a standard deviation. So this connection allows us to connect basically connection allows us to connect deep learning to Bayesian modeling, the Bayesian probability theory in a principled way. And this mathematically grounded connection gives us a treasure trove of lots of research opportunities like uncertainty in deep learning models, interpretability in AI safety, principled extensions to deep learning using tools and statistics, enabling deep learning in small data domains, and so on. But before we're gonna talk about actual applications, let's try to get an idea into how this connect. Like, what does that connection mean? So for that, we need to talk about Bayesian neural networks. A Bayesian neural network is a very simple tool. It's a neural network where you put a distribution over the weights. So we had W was before just a weight matrix. Now W is a stochastic weight matrix. That's the only difference. We have basically put a prior distribution P of W over each weight. Now, if you also give me another distribution likelihood, P of Y, what's the probability of Y conditional on some W and X, then I can find the posterior. I can evaluate what are the more likely and less likely weights conditioned on some data that you gave me. Issue is that evaluating this posterior is very difficult. Many great researchers have tried to do that over the past, I think, almost 30 years now. I'm going to talk about a very simple way, which is you define a simple distribution Q, and try to approximate that distribution. Try to find the distribution Q that will approximate this nasty posterior. So Q is going to have some parameter M. This is a nasty posterior that we have, which is very difficult to evaluate. This is Q, some parameter theta 1. I'm going to wiggle this theta 1, theta 2, theta 3, optimize that theta until these two distributions match together. That's basically approximate variational inference in a pictographic sense, in a pictographic depiction. And it turns out that if you define your Q to be of this structure, which is really not that important, then the optimization objective of stochastic variational inference with this Q distribution in this Bayesian neural network model, in this model, is identical to the objective of a dropout neural network. Now that basically means that implementing approximate inference in a Bayesian neural network, in a Bayesian probabilistic model with this Q distribution, is identical to implementing dropout training in your deep learning model line to line. You will be implementing exactly the same code with some important caveats, which we'll talk about later. Caveats about like how do you tune the dropout probability specifically. So what does that mean? That basically means that we can get model uncertainty using dropout, or in more practical terms, means that if you give me an input X, then I'm going to feed that input X through the model, do a stochastic forward pass. I'm going to do dropout at test time without updating the weights, just do stochastic forward pass. I'm going to get some output Y. I'm going to feed the same input X, do another stochastic forward pass, get a different output Y with a different dropout mask. Do that 10 times. I'm going to get 10 different stochastic outputs. I'm going to look at the mean and standard variance for those 10 different outputs. And that's all. And these are the 4 lines of Python that you need to use in order to get uncertainty in deep learning. It's not necessarily going to be good uncertainty, but these are the 4 lines of code that you need to get some uncertainty. And then if you actually want to make sure that's going to be good uncertainty, then we can talk about that more later. What does that uncertainty look like? So if, let's say you give me the CO2 levels in Mauna Loa, Hawaii over the past 20 years, past 40 years, and you ask me what will be the CO2 level in 20 years' time. If I take the data, normalize it, center that, over here I fit a 4 hidden layers, 1024 units, balloon activation neural network, then it fits very well to the data. You ask it the CO2, what will be the CO2 level in 20 years' time? It's going to give you this prediction that makes no sense. Now, I can take exactly the same network, use these 4 lines of code now, exactly the same this network with dropout as well, like normal way that we use dropout at test time. Use the same network, just use the different evaluation at test time, we're going to get this. Now, prediction still makes no sense whatsoever, but the model also tells us I have no idea what's going on. You can see that each half standard deviation is a different shade of blue. The model basically says it could be anywhere over here. If you ask me the CO2 level in a year's time, I will tell that and I will be a bit more confident. So what can we do with that? We're going to look at some examples. What's the time? We're going to look at a couple of examples on doing deep learning, human in the loop, and we're going to look at how to do deep learning in scientific applications, where we actually need to get confidence bounds. So I'm going to do a very abrupt shift. We're not going to talk about machine learning anymore. We're actually going to talk about astronomy for a bit. This is the Northumberland telescope that was donated to Cambridge by the Duke of Northumberland in 1833 for the foundation of the new astronomy department. This is an actual print of the telescope from illustration from 1843. This is a picture from a couple of years ago. It still looks very much the same. At the time, this was the world's largest refracting telescope. Now we're going to fast forward 200 years. This is the Arecibo Observatory in Puerto Rico. This is a picture actually I took a couple of years ago in a project that we have with them. This is the primary dish. This is the receiver, that's the transmitter. This is the platform. There's a person walking on the platform over here to give you a sense of an idea for how big this thing is. That's not the person. This thing over here is like 4 times the height of a person. There's like these are huge trees at the back. That's the control room with all these different things. So this was the world's largest single aperture telescope. And even that is already superseded by even a larger telescope. I hope you're getting the idea that these telescopes are becoming larger and larger, and what we do with these telescopes is collect lots and lots of data. So this is basically this is the output from these telescopes. These sky surveys, either looking at looking for targeted sky surveys, looking for specific targets, or just like scanning the sky, collecting lots and lots of data. And from these sky surveys, we get astronomical catalogs, where we take all of these different objects in the sky, and basically we say each object, what are the properties for that object, what are the coordinates, if that's a galaxy, what's the morphology for the galaxy, redshift, and so on and so on. Now, as you can imagine, back in the days when you just had a person sitting making observation and like taking some notes and then sending that to a journal saying I found a new planet that has this and these properties, it's very different from when you have these huge telescopes where it's basically infeasible to do manual labeling for these things anymore by scientists. So basically that's why new projects started, like the Galaxy Zoo Citizen Science Project. which is, I think, one of the largest citizen science projects in the world, where they basically get volunteers to sit down and label galaxies. You can actually go on their website, and you can basically, it will show you a galaxy, and it will ask you, is it smooth, is it featured, is it an artifact? Basically, it will calibrate you, and it will get you to a point where you can actually start labeling these things. And then from these, we collect these astronomical catalogs, and that's basically what we use to do science in the field of astronomy. Now, as you can imagine, even that is becoming too difficult, because with the new sky service that we have, like the squared kilometer array, we have millions and millions and millions of new observations, and it's infeasible to even get humans to label, or it's infeasible to get humans to label all of this data to build the catalogs. So what instead we can do, we can use an active learning. We can use a human in the loop approach, where we get machine learning model trained in some labeled galaxies, like we tell it, oh, that has property A, B, and C. We take the large set of huge billion unlabeled galaxies, and basically we evaluate something called an acquisition function on this unlabeled set. An acquisition function tells us what are the most interesting points that we should ask an expert to label. We're gonna collect only the points that have the highest acquisition function. You're gonna ask an expert to label these, add that back to the training set, and then retrain the model, then continue this cycle. That's called active learning. We're gonna switch back to machine learning and talk a bit more about active learning in the context of the tools that we talked about earlier today. So, what's a good acquisition function? And one possible choice for acquisition function would be one that maximizes uncertainty. What basically model doesn't know. But what type of uncertainty? Apparently there are actually different types of uncertainty, which we didn't talk about, but there's something called aleatoric uncertainty, which captures noise inherent in the data. There's epistemic uncertainty, which captures a model's lack of knowledge. Fun fact, aleatoric actually comes from aleator, from Latin, dice player. Basically, if you throw a pair of dice every time, again and again and again, there's always going to be some stochasticity in the process. You're never going to reduce the amount of noise that you have. So that's basically aleatoric uncertainty. For example, it comes from noise inherent in the data, measurement, observation noise, and so on. Epistemic uncertainty actually comes from Greek, episteme, knowledge, literally means knowledge uncertainty, where it's uncertainty that if you get more and more knowledge, you basically reduce that uncertainty. So just to see how much you've been listening, so we have two plots over here. One has highest epistemic, one has high aleatoric uncertainty. Who thinks this one has high epistemic uncertainty? Show of hands. Who thinks this one has high epistemic uncertainty? Very good. Yeah. So over here, we have a gap in the data. Basically, we have lots of possible explanations. If I give you another data point x over here with a y value, then I will collapse that uncertainty. Basically, all of these different, you still have variability over here, but all of these functions will go through the new data point. On the other hand, over here I have an example of actually very much know what the underlying function is. It's just that every time I draw a realization for that function, I'm going to have lots of observation noise added to those realizations. So, which one would you use for active learning? Which one would you use in order to decide where to acquire new data points? Any preference? Let's try to get a bit more insight into what's going on, into these different uncertainties. So let's say that we have the three different models, M1, 2, and 3, that classify dogs versus cats, and I give it some picture X, and I feed that picture X for M1. I'm going to get a bunch of stochastic forward passes, or draws from the predicted distribution. Every time I feed the same input X. Model 1, I'm going to get 10, 10, 10, 10, 10. Model 2, I'm going to get 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, every time I draw from the distribution. Model 3, I'm going to get 10, 01, 10, 01, 10, 01. Model keeps jumping back and forth. Which model do you think has high epistemic uncertainty over here? Who thinks that model 1 has high epistemic uncertainty? Who thinks that model 2 has high epistemic uncertainty? Who thinks that model 3 has high epistemic uncertainty? Yeah, I got answers all over the place. So let's try to get an idea. Let's try to drill down a bit more and understand like how does epistemic uncertainty, what does it look like? How do we actually get that? Weirdly enough, like especially in classification, in regression it's very easy. In regression, obviously, you would use this for active learning because you have a gap in the data. You would want to get a point over here, basically, so you know exactly what the label should be. Classification, it's much less trivial to decide what is a good way of measuring our uncertainty, what is a good way of defining our acquisition function, what are interesting points. So let's try to connect intuition from here, from regression, to the case of classification. So let's start from a point over here. So I have a point x over here, which has corresponding y over here. I feed that input x through the model. I'm going to draw a function. I'm going to get value over here. I'm going to feed it. How do we do classification? We basically take regression model and stick it for a sigmoid function, a squashing function. A function that takes large values and gives us a vector 1, 0, large negative values and gives us a vector 1, 0, 1. So I take a point over here, sample a function, sample the red function, evaluate the point at the red function, I'm going to get a large value. Squash that, I'm going to get 1, 0. Sample another function, green function, evaluate the same point at the green function, get the same exact value. Squash that, again I'm going to get 1, 0. So every time I basically sample a function from the predicted distribution, I'm always going to get 1, 0, 1, 0, 1, 0. So that basically corresponds. This model with the point over here corresponds to the case where I'm actually very confident about my prediction. And actually I know exactly what my prediction should be, and I don't really need to collect more data points over here. I should have zero uncertainty. Now let's look at this, like this case. When does this happen? 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. So let's say that this is like y equals plus 100. This is y equals minus 100. This is y equals 0. I take an input x, sample a function, sample the green function, feed it through the function, I'm going to get 0. Squash 0, squash the number 0 for a sigmoid, I'm going to get 0.5, 0.5. I'm going to take the same input x, feed it, sample another function, sample a red function this time, evaluate the input x at the same red function, at the red function now, I'm going to get the same value 0 again. Squash it for a sigmoid, I'm going to get again 0.5, 0.5. So every time I sample from the predictive distribution, I'm always going to get 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. I don't really need more data over here. You actually see that I know exactly what the value should be. I know that it should be 0.5, 0.5. I know that if this is an inherently ambiguous point, or point that has inherent noise in the data. For example, a point for which the labels were both 1 and 0. So the log likelihood maximizer, or the loss minimizer for coarse entropy loss, would actually be predict 0.5, 0.5. It's fine if you didn't follow the last point. Now, when would this happen? Let's say I take a point x over here, and I sample a red function. I'm going to get a high value. Squash that, I'm going to get 0.1. Sample another function. I'm going to get the green function. Feed this input x for the green function. I'm going to get a large negative value. Squash that, I'm going to get 1, 0. So every time I sample a new function, my prediction is going to flip 1, 0, 0, 1, 1, 0, 0, 1, 0.9, 0.1, 0.1, 0.3, 0.7. My predictions are going to be all over the place, basically. So actually, this model, this case over here, this input x with this specific model, which is the same as input x over here with this specific model, corresponds to having high epistemic uncertainty. And this corresponds to actually having low epistemic uncertainty. And this is very certain that we know what the answer is. So a way of measuring the whether we actually get this behavior or this behavior, we can measure that using tools in information theory called the mutual information between the model parameters and the label y. The paper that suggested that was actually called Bayesian active learning by disagreement. A paper that suggested using that for active learning and suggesting a tractable way of computing that. So that's why we call that bold over here. And we can actually see that if we look at x-axis, so this is MNIST experiment. If you look at x-axis, is number of acquisitions. So we start with only 100 labeled data points from MNIST. Over here, we have 1,000 labeled data points. And we can basically see that by actively acquiring the points that model tells us are interesting, then we can actually converge you can basically get much better results than just randomly selecting a data point and basically uniformly selecting a data point and asking an oracle, give me a label for that. Or if you ask for how much data do we need to get to 5% error on MNIST, then we need 300 points compared to 800 points if you just randomly select data points from the dataset. So let's switch back to astronomy. We have over here the same application from before, Galaxy Zoo. Now we're gonna basically look at, can we do the same ideas for active learning, to do actually human in the loop for Galaxy Zoo, for morphology classification. So this is actually work that we've done with the guys that did Galaxy Zoo. This was published at the Royal Astronomical Society only a couple of months ago. So this is work with Louis Smith, Mike Wormsey, Chris Lintott, and the Zooniverse Citizen Science Project members. And this is actually deployed. So if you actually go and try to basically take part in this citizen science project, then you will be using the tools that we talked about. So this is actually very interesting. So we have two plots over here. Both of these plots, the x-axis, we have the number of acquisitions, this time in thousands. The y-axis over here is the training loss, basically how surprised you are about the data that you've seen. So if we just randomly select from the dataset, we're going to select most of the uninteresting, like most galaxies are not that interesting. Most galaxies basically just look like blobs. And if you just randomly select from the dataset, you're going to select mostly the uninteresting galaxies. So the baseline uniformly selecting from the dataset, randomly select the dataset. Model is never actually gets surprised. But if you actually use the active acquisition, active learning tools that we talked about, then every time you could make an acquisition, the model gets very surprised, and then and now I know what that is. Oh, that's very surprising again. Okay, now I know what it is. And if you look at the evaluation set RMSE, then we can actually halve the number of samples that we need to get, half the number of volunteers that we need to get to the same accuracy for this model. For this model specifically for morphology classification. One last interesting observation is that if you look at the smoothness of the galaxies and randomly select from the dataset, when model mostly selects the smooth galaxies, so the random acquisition mostly selects the smooth galaxies because that's the majority class in the dataset. You don't know the pull points, you don't know the labels for this, you don't know which are the interesting ones, which are the not interesting ones. If you randomly select a pull point, then most likely it's just going to be smooth and not interesting. And then you only know that after the volunteer already labeled that. But if you use active learning and specifically look for points the model finds surprising or confusing or has high uncertainty about, it actually really doesn't like the smooth points, much more likes the non-smooth points, like the featured galaxies. So this is, any questions so far about active learning, by the way? In that case, I'm going to make another sharp transition to a completely different field in astronomy. Meet WASP-12b. WASP-12b is an exoplanet orbiting the star WASP-12. It was discovered in April 2008. Its distance is 1,410 light years away from us. And working with the Hubble Space Telescope, scientists discovered that reported that detected water in the atmosphere of this exoplanet. So I was actually very curious about how do we actually tell whether we have water in these very, very far exoplanets. And it turns out that what we do is we take the spectrum from the Hubble telescope, and what we do is basically we fiddle with the parameters. We have, if you tell me what the atmospheric parameters were for the exoplanet, like the amount of water and the CO2 and the temperature and the cloud coverage for the exoplanet would be, then I know how physics work. I know what the spectrogram should be in that case. I know what the noise that I have in this Hubble Space Telescope looks like. I know what the spectrum should look like. So what we do is basically say, okay, let's try one atmospheric composition, feed it for the forward model and see does it match the model spectrum. No. Okay, let's try another atmospheric composition, feed it for the forward model, does it match the observed spectrum? No. Do that again and again and again, basically fill it with atmospheric parameters, or in a more formal language, use nested Monte Carlo sampling, which is basically fiddling with the model parameters, until you manage to find a good enough atmospheric parameters that actually match model spectrum. What you can do instead, you can just learn an inverse model. Then basically generate lots of possible atmospheres, feed them through the Ford model to get the spectrum, and train a neural network for the inverse model to map from the spectrum back to the atmospheres. Now over here we have observation noise in the Ford model, so we actually know that we have noisy data. If the observed spectrum, so if you give a spectrum that we never saw in the training set, then I must be able to tell you that this is something I've never seen before. I don't want to tell you, oh, there's definitely water on that exoplanet just because I'm extrapolating confidently to some new spectrum. So this is a very good tool, opportunity to use these tools for Bayesian deep learning, where we build a model that takes a spectrum, feed it through some dropout model, some dropout layers. It's not important what concrete dropout is. Spits out the mean for the atmospheric parameters and the covariance matrix. So basically, we learn the observation noise in the data as well. So we have a heteroscedastic model over here, and then we draw atmospheric parameters. Now, how do we tell if our model is good or not? We take a validation set from the synthetic data that we generated from this synthetic data, and we evaluate. We basically take that validation set, feed it through our model, and see, can we actually reconstruct the concentrations for the different compounds correctly. So basically you can see, yes. You can look at that visually as well for different compounds, water versus CH4. Basically we can see at the posterior distributions. We can actually look at what are the confidence, it's not confidence, basically it's looking at the actual predictive distribution, or in the field they call that the posterior distributions. Over here, in our case, it is an actual predictive distribution. For how much do these different quantities correlate with each other, and how much do they actually match the ground truth that we have in the generated data. And we have these very nice plots. So this is actually work that was done together with Adam Cobb and NASA Goddard while at NASA FDL, and this was published at the Astronomical Journal a couple of years ago. And we can actually evaluate this model on the actual WASP-12b planet that we saw before, exoplanet that we saw before. We can actually see, look at that, we have water in the exoplanet. Last example that I have over here is actually not in space, but from space. And now the machine learning actually lives in space, literally lives in space. And this application, we basically looked at flood detection. So floods have always been a big issue, and like in recent years, they've basically become more and more devastating, especially when we have urbanization for lots of areas that usually used to get flooded before. So these are actually pictures from all over the world, including, I think in Malaysia, including in England, I think that's in Scotland. When you work with first responders, you need basically to give them some useful information into where do we need to send help. So over here, we have an example of what a flooded area looks like compared to when it's not flooded. So you can actually see that a lot of the water kind of looks quite difficult to spot. And what they do at the moment is basically they take these pictures of before and after, commission a satellite, and get someone to sit down and do the data processing to give them a flat map of basically saying this is water, not water, water, not water. Based on that, first responders decide where to send help. The issue is that is a fairly time-consuming process. When you need to commission the satellite and you need to get the data down, even though we have these agreements to get satellite time for emergencies, to get data down, you have to wait until the satellite goes over a ground station, sends all the raw data down, which is a lot of data. Then you need to get a scientist to come to the office and basically start processing the data. And then you need to send it to the first responders. And you can imagine that can take some time. And that can take quite a bit of time, especially if it's in developing countries like in Africa. So in this project specifically, we looked at how can we reduce the time from disaster to data? How can we get data to the ground station faster? And how can we accelerate or automate the image processing pipeline? So the idea over here is specifically to look at processing on board on the actual satellite itself, rather than doing the processing over here. Why? Because that allows us to send down much less data. So if I only need to send you 1 bit per pixel of yes, no, is that pixel flooded or not, then I need to send you much less data, and I can actually use CubeSats, in which case I can use constellations of CubeSats that will be monitoring 24/7. And then I can use an antenna in the field rather than using these huge ground stations. That then I can actually send the data directly to the people that first responders in the field itself. So in this project specifically, we looked at how can we take these huge segmentation models we talked about before, compress them, do pruning, get them to a point where they can actually run on embedded device, an actually embedded device that we have running on the satellite, showing that we can actually get trustworthy segmentation apps for flooded areas from CubeSats that could be used for flood intelligence. Reduce the downlink, and the idea, basically working with the FSS CAT mission, the idea is basically to deploy that on the FISAT-1 satellite in early 2020. So this was work done with Louis Smith and many other great collaborators and European Space Agency while at FDL Europe. Yeah, so I think we're on time. So there's still lots of other opportunities for research in this field. I mostly talked about applications and applications in astronomy, but we have lots of other applications in autonomous driving, medical applications, safe enforcement learning. We have lots of new tools, new opportunities for new tools motivated by these different applications. So when you work with practitioners and they tell you, oh, your tool doesn't work over here, then basically that gives you an opportunity to develop a new tool, to develop new ideas and statistics. So we have lots of opportunity to develop new tools and help others build safe and robust machine learning for responsible deployment in industry and in academia. That and much, much more. Thank you very much for listening. If you want to hear more, there's go on the website and have a look at the stuff that the group has done over the past few years. And yeah, that's all. Thank you.
Very much. I have time for questions.
Hi, thanks for your talk. And in your slide 8, did you mention a result about dropout and its equivalent?
Which one are you looking for? Is
please.
mic on?
Sorry?
Is the mic on? Oh, maybe get it closer to your
Yeah,
mouth.
maybe.
Yeah.
In your slide 8, do you mention some result about equivalence with dropout layer? And that
Oh.
number 8, please.
8.
Yes. That one.
Yeah.
Okay. And implementing inference with this prior. When you mention this dropout training, it's just one layer or the whole dropout procedure in all the model?
So just to be clear, this is not a prior. This is approximating distribution.
Okay.
The prior is actually this thing, which is P, which is
Yes.
something I didn't define explicitly. So in this case, actually, is well, in the example set I talked about, prior is actually an isotropic Gaussian distribution with some fixed width, and the width actually determines the smoothness of the function. So if there is if it's a very wide Gaussian prior distribution, that basically corresponds to having very slow varying functions, very smooth functions. And if your prior is very narrow, then that corresponds to having very erratic functions that can change very quickly. This is approximation to the posterior, which is this thing. This is just a simple depiction for what it would be. So this is for a single weight matrix. If you have multiple weight matrices, then it will be basically the product probability of the product distribution of all these probability measures.
So I have one. in your exoplanet example, you try to find some water, if the atmosphere gets water or not, but how do you train your machine on what is an atmosphere with water? You simulate them, or because I think we don't have many atmospheres with water now in there.
So in that case, scientists have a broad idea for what are the different compounds that stars are made of and what planets will be made of. In which case you can basically generate lots of possible atmospheres based on these different possible concentrations for the compounds. And then from these, you feed them for the physics model, and then it basically tells you what the atmosphere would look like. Now, the biggest issue is actually what you said, is that if you have an atmosphere that you didn't think about before, as, oh, I didn't know that's something that I could actually have as for an exoplanet, then you would not do that a priori. You're not going to have that in the data set. If you actually have an exoplanet with that atmosphere, you're not going to find that if you just use a naive inverse model that just tells you, oh, this is some compound that this thing corresponds to. You can actually take that, you feed in the spectrum, model spits at a concentration for the different compounds. You can feed that back through the forward model and see, actually, no, it doesn't match my spectrum. That's basically why you want to use these Bayesian deep learning tools, because the model actually tells you, I've never seen that compound before. I'm not going to guess what atmosphere, I've never seen that spectrum before. I'm not going to guess what atmospheric compounds it corresponds to. So that's basically the posterior distributions that we have in the parameter space.
Can you go back to the slide where you have the plots after the colorful, more the ones with the synthetic data after, oh, more there. Well, the next one. I didn't quite get what's that? I mean, can you explain again, please?
So we have on the x-axis over here the possible concentration for, well, this is the temperature in Kelvin, this is the concentration for water, concentration for HCN, for NH3, and this is the cloud coverage that we have. We have the same concentrations on the y-axis, and then basically the model spits out every time you do a forward pass for the model, it spits out a point, which is a configuration of different concentrations.
Okay.
And that point basically would have temperature, water, cloud coverage, so on and so on.
These are
So
synthetic data, right?
Well, that's actually no. That's the
They're the real.
That's actual exoplanet atmospheric. So that's actual exoplanet. What is it? Spectrum.
Okay.
That is fed through the model, and then you do one forward pass, and you get a point over here, which is the concentration for water and temperature. And that point also corresponds to a point over here, which is the water and HCN, and water and so on and so on. Then you do another forward pass, and you get a point here. Another forward pass, you get a point here, and so on and so on and so on. And basically this blob over here captures the correlation between the temperature and the water, and this how spread it is how certain we are about the temperature, for example, about the water. So you can see, like, we are fairly uncertain about the HCN concentrations, we are fairly certain about the temperature and the water composition, water being very much non-negligible and temperature being around 1000 Kelvin. Cool. If there are no more questions, then thank you again. Oh, there's another question. Yeah.
Yeah, thank you. The advantages of using Bayesian deep learning are kind of clear, especially in scientific applications when point estimates might be completely wrong. But I'm wondering about the computational cost. I mean, how much expensive it is to train something that is going to give you this kind of confidence intervals with respect to training a regular deep neural network.
So the alternative over here is literally use nested Monte Carlo sampling. Nested Monte Carlo sampling takes hours and hours and hours for a single exoplanet. So if you compare, basically, if you say I'm not going to trust a single point prediction, what are the tools that I have available? Then you can either look at multi-cloud techniques, which will take hours and hours and hours, or you can look at approximate inference techniques, which is literally what we talked about over here. That will take a few milliseconds. I mean, you do need to do multiple forward passes, but each forward pass takes a few milliseconds. So doing that thousands of times for a single spectrum will still be negligible. Yeah, there's another question over here.
In your implementation of the images from the sky and radar in space, what happens if the people in the street right there in the street don't see that there's a flood coming, but the image or the sky tells that there's a storm, but there's no flood in there because you cannot see if there are clouds? How can you tell if there's, or how can you fix that things?
So, not this project, but actually a project that we did with USGS this year as well, as part of FDL, NASA FDL, was looking at flood warning systems and looking at gauged and ungauged river basins, where basically you have a river and you want to predict whether you're going to have a flood in that river given recent precipitation, recent rainfall. And we actually found that using satellite imagery as well as a bunch of other ground truth data, like observations from the rivers themselves, the idea is mostly to be able to do that in cases where you don't have a sensor in the river. So using the satellite data, you can actually predict very well an hour in advance whether we will have a flood in a certain area. And we actually found that we were more precise than NOAA, which is the North American flood prediction system. We found that we actually were significantly more precise in predicting floods, both in terms of false positives and false negatives. The ROC plots were surprisingly good, actually.